Hello, in this video I'm going to show you how to calculate the electric field at some point between two charged plates. So let's take a look at our situation here. We've got a charged plate over here, and this is positively charged, so it's got a positive Q charge on it. And then there's another plate that has exactly the same magnitude of charge, but it's negative, and that's over here. And both plates have an area of A. Now, somewhere between these two plates, and I haven't told you exactly where, but it doesn't matter for right now, there's a point, and I want you to tell me what the magnitude of the E field is between those two plates. Well, how do you do that? You're going to do that using Gauss's law. Now, before we get into Gauss's law, first let's make sure we understand what the field lines are. So the field lines are basically drawn in the direction that a tiny positive test charge would move. So if I put a tiny positive test charge right here near this positive plate, what would it do? Because it's positively charged and the plate is positively charged, it's going to run away. So it's going to move in these directions, and it's going to be attracted to the plate that has negative charge on it. So that's how we define the E field direction. These field lines point in the direction that a tiny point charge would move. So they're all going parallel like that, from one spot on the left-hand plate to another spot corresponding to it on the right-hand plate. Those are the field lines. Now that's going to become important because when we pick a Gaussian surface to enclose all this charge here, we want to pick a surface that is always going to intersect the field lines in a perpendicular manner, so that all those field lines are penetrating the Gaussian surface at a 90-degree angle. So how do we do that? Let's look at Gauss's law. This is the equation again, and what it's saying is basically that E times the area of the Gaussian surface is going to equal Q enclosed, the amount of charge that's enclosed in my Gaussian surface, divided by this constant epsilon naught. This perpendicular means that the field lines will have to go perpendicularly through the surface that I pick. That's how we're doing it in this course, P202, with algebra. It is possible to do it in such a way that you don't have perpendicular lines, that they're coming through at some angle, but then you got to take the cosine of the angle, and that's really messy. In this course, we're just doing it in a quick and easy, simple way for simple cases where you can construct a Gaussian surface that will have perpendicular field lines. So again, what we're trying to do is we're going to solve for A, we're going to divide both sides by A and get E by itself on the left-hand side of the equation, and we'll get a formula for the electric field between the plates. So let's do this. So we've got to pick a Gaussian surface. So how do we do this? We can pick a Gaussian plane like this, okay? So it's a plane such that every one of those field lines intersects the plane at 90 degrees. So then we have E perpendicular. The field lines are going perpendicularly through the Gaussian surface that I've picked. Now, if I picked a sphere or something like that, it wouldn't be going through perpendicular all the time, and that would be messy and harder to deal with. So I just pick it like this. Now, this Gaussian surface, I haven't really drawn it completely, but it's going to go back slightly behind this plate and enclose all the charge that's on that plate. So it's really kind of like a box that goes around that. But since all the field lines are going perpendicular to this plane right here, and they're not going out this side or that side, then it doesn't really matter. I don't have to worry about field lines going out the back or up the top or anything. All the field lines are going in this direction. So they're only going through one face of this box, and that box is going to have an area A, exactly the same area as these plates. So the next step is pretty easy. All I want to do is I want to isolate E by dividing both sides by A. And I do that right here. And that's all there is to it. E then, the electric field, at any point between these plates is going to be the charge that's enclosed by that Gaussian surface, so that'll be positive Q, because that's all the charge on that plane, divided by A times epsilon naught. I just divided both sides by A, and now I get this formula. Now notice something about this formula. It does not depend on the distance between the plates, right? So what that means is that the electric field is the same here, as it is here, as it is here, anywhere in between these two plates, if the plates are very, very large. So imagine they're infinite in size. So we're going to ignore edge effects that happen around the corners or the edges of the plate. But if it was very, very large, in the limit, that's what we're going to get for the equation that describes the electric field. So now let's apply it in a concrete example. So let's say we've got something like this. I could potentially give you an exam question where I want you to calculate the electric field between these two plates. And I'd give you the charge of this, I'd give you the area of that, and so forth. And then you'd have to calculate these charges, or the electric field given these charges. So imagine I gave you 1.3 picocoulombs is on each plate. Imagine the area of each plate is 2 square meters. And then epsilon naught, we would always give you this constant, 8.85 times 10 to the minus 12th farads per meter. We'll get into farads in a little bit, but don't worry, these units will cancel in this problem. So here's the situation. How do I apply it? How do I calculate that electric field? Well, I'm just going to plug these values into this formula in the box here. And so we do that right here. So this is Q right here, 1.3 times 10 to the minus 12 coulombs. This is A, 2 meters squared, and this is epsilon naught. And we plug all these guys in, we get 0.037 newtons per coulomb. That's the electric field right here in between the two plates. It'll also be that right near the surface of this plate, and it will also be that right near the surface of this plate. It's independent of distance because R doesn't appear anywhere in the equation. Now, if I change the area of the plates, that could change the electric field. Notice that if I make the area bigger, leaving Q constant, then the electric field will get smaller because the electric charge is going to be spread over more area. Or if I leave A constant but increase Q, as I make Q larger and larger, the field will go up. So you should also be prepared to answer some kind of questions based on this sort of qualitative understanding of the formula. How would the electric field strength change if I increased A but kept Q constant? Or if I increased Q but made A constant? These types of things you should be able to know, just in case I ask them on the exam. Hopefully this has been helpful to you.